Yellowstone was the first national park to be established in the United States, and for good reason. It is famous the world over for its spectacular landscape of geysers and springs. It is also a massive volcano, the largest volcanic system in North America. Yellowstone's volcanism is what gives rise to its unique geothermal features. Yellowstone Park sits on top of a massive volcanic hotspot. Models suggest it is fed by a plume of hot mantle rising to the surface. This hotspot is located under the Yellowstone caldera. A caldera is a bowl-shaped depression that forms after a volcano explodes and rapidly empties its magma chamber. It is a kind of sinkhole. The Yellowstone hotspot hasn't always been situated under Yellowstone Park. This is because the lithosphere is sliding over the hotspot. The lithosphere is made up of tectonic plates. The plate located over the Yellowstone hotspot is the North American plate, and it is moving southwest at a speed of about an inch per year. We know this because the hotspot has left a path of destruction as the North American plate has slid across it. A chain of calderas and lava fields were left by hotspot eruptions over the last 16 million years. This hotspot track forms the eastern half of the Snake River Plain, a depression that stretches from one end of Idaho all the way to the other. One of these hotspot eruptions happened about 12 million years ago. The resulting ash was blown easterly for hundreds of miles. In Nebraska, this ash drifted to a depth of over 6 feet, covering and suffocating a large number of animals who were at a watering hole. Animals like rhinos and camels were extremely well preserved in the ash. The site is famous for its fossils, offering a rare snapshot of the Miocene era in North America. It is also evidence of the kind of far-reaching effects that are possible with a Yellowstone hotspot eruption. The hotspot now sits under Yellowstone Park. It formed the Yellowstone caldera when it erupted about 630,000 years ago. The eruption that formed this massive 45-mile-long caldera was a magnitude 8 on the Volcanic Explosivity Index. 8 is the scale's maximum value, representing a mega-colossal event. In the mantle plume model of the Yellowstone hotspot, hot rock rises up from the mantle. The Earth's crust is largely made up of silica. You might know silica as quartz in its crystalline form. Silica is known for its hardness, and so when the crust melts and forms magma, it is thick and stiff. Gases can't get past it and escape to the surface. The resulting eruption is powerful and explosive. This could be why the eruptions caused by the Yellowstone hotspot have been so big. To better understand these forces at work under Yellowstone, scientists needed to be able to see inside the hotspot itself. So, they used seismic tomography to create a three-dimensional map of the plumbing system beneath Yellowstone. The resulting images reveal that there are 2 magma chambers under Yellowstone. One only about 6 miles down, and another one at a depth of about 19 miles. The deeper one is also enormous. The hot rock inside it would fill about 11 Grand Canyons. The image gets fuzzier the deeper we go, but there's evidence that the mantle plume is a long, thin-tilted tube that extends from the hotspot all the way down to the lower mantle. By having a clear picture of what's happening under Yellowstone, scientists can better assess its volcanic hazard. From seismic tomography imaging, we can see that the rock in the uppermost magma chamber is not entirely filled with melted rock. The rock is hot, but mostly solid with pockets of molten rock. The rock in the deeper chamber is only partially melted too. Gazing into Yellowstone's depths, we can not only keep tabs on potential dangers lurking below, these imaging studies also help us understand the forces that fuel the park's spectacular geothermal wonderland.